Okay, this is a Newton's second law problem with one object, but in two dimensions. Um, the webcam looked pretty choppy on the last one, so I'm just not going to use it anymore. So, here we go. Here's my object. I've got a crate or box on the floor, and it is being pulled to the right by a force of 5 newtons, being pulled like to the right and up a little bit. And I would like to know the acceleration of this box. Um, yeah, that's kind of it. So, number one thing, I need to establish some directions. So, just for fun, I'm actually going to go like opposite the last time. So, I'm going to make to the right negative and the left positive, and I'm going to make up negative and down positive. Remember, these are just choices, and it does not matter what you choose as long as you stick with your choice and the consequences it brings later. So, okay, step one, I've got a diagram with the directions. Step two, I need a free body diagram. So, here's my crate. It is a 20 kilogram crate. Okay, I need some axes on this thing this time. Definitely need them because there's an angle involved. I need to put directions on there. So, up is going to be negative y, down will be positive y. Whoops, I don't know why I just did that. Because it's getting late, that's why. To the right, we're going to make that negative x, and to the left, we're going to make that positive x. Okay, now I need forces. Okay, so in my head, my checklist is there gravity? Yes. I mean, I'm assuming we're on the planet Earth, so gravity is always down. Draw the force of gravity pointing down. So that is m times g. So for this one, that is, 20 times 9.8. You know what, I'm just going to jump to that. It's 196. Yes. Yes, 196. Ooh, you just heard me drop my calculator. Okay. Okay, so is there gravity? Yes, draw it. Is there anything touching this box? Well, whatever's causing this force is touching this box, so I need to put that on there. Let's do that. I've got a 5 Newton force making an angle of 35 degrees with the horizontal. And you know what else is touching this box? The floor. So the floor is going to exert a force on this. That is a normal force. Normal forces only push, so the normal force has to push away from the surface, so this is going to push up. Normal force is always perpendicular to the surface, so if the surface is horizontal, the normal force should be straight up. That's supposed to be straight up. I didn't do a very good job, even with graph paper. Okay. Anything else touching it? No, so that should be it. Do I know the normal force right now? No, I don't. You may be tempted to write that it's the same as the weight. That is not true for this problem. The normal force is whatever it needs to be so that this box doesn't sink into the ground. Okay? And for this problem, we don't even really need to know what the normal force is, although I think I'm going to go ahead and find it anyways. And you know what? Actually, let's make that part of the problem. What is the normal force? That's going to be the other questions. Two questions. What is the normal force? What is the acceleration of the box? Okay. This is my free body diagram. It's ready to go. Okay. Next step. And we didn't have this step on the last problem because we didn't need it, but the next step is to break down any vectors that you have into its component parts if necessary. So for instance, this 5 Newton force, I need to break it down into its x and y components. So there's going to be a component here. Please note that I'm using a dotted line because this component is not a new force on the diagram. It is it's just the one force that I already have that I'm breaking into components. Okay, so that's going to be Fx right there. And I use red for y. Here's Fy. Got a nice little right triangle here. So Fy is going to be, let's say it's opposite the triangle. So this is going to be the hypotenuse, which is 5, times the sine of the angle. And hang on, just leave it like that for now. We have to be careful with signs later. And the screen is kind of bright. Hang on. I don't like it being this bright. We're gonna tone that down a little. Yes, that's better. Okay. It's both bright and hard to see, which is terrible. Okay. This one is adjacent to the angle, so we're going to be hypotenuse times the cosine of the angle. Okay. If we had more, I'd do them all. Okay, break down anything that's at an angle. Okay, that's step 2. Step 3, now we go back to the same steps that we had when we were doing one object in one dimension, and that is to write down Newton's second law in component form. So F net x equals max, and get that out of the way a little bit, and it doesn't want to go, never mind. F net y equals may. Let's write those down. Then you're going to fill in what you can. Okay, so for instance, in the x direction, well, the only force that's in the x direction is Fx. That's it. Basically, I've replaced the 5 Newton force with the components of it, so I'm ignoring the 5 Newton now and just focusing on the components. And of everything that's drawn here, the only thing that is in the x direction is the 5 cosine 35. But I gotta be careful, because that is pointing toward what I called the negative side. So when I go to fill in F net x over here, I need to fill in minus 5 cosine 35. That's what I need to fill in. If I had more forces, I'd have more over here, but there's just the one, so that's all I've got. On the right hand side, I fill in the mass because I have it, and then ax I don't know. So that's it. That's all you can do. Just leave that for now. Okay. I guess if you wanted to, you could solve for ax right now, but I'm just gonna wait until like the more appropriate time for more general problems. So just leave that. That's one equation. F net y, I do the same thing. Now, here's where something becomes a little bit, I need to make a stipulation. I'm going to assume, well, mathematically it does work out this way, but I'm going to assume that this box doesn't leave the ground, okay? It does not leave the ground. Wow, I can't write anything. Okay, that's going to be important in a second, and usually you can assume that, although I'll show you how you can tell in just a second. Okay, basically we're going to assume it doesn't leave the ground, and if that's not true, there'll be something very obvious that happens, and I'll tell you about it when we get there. Okay, so F net y, looking at the y direction, I've got normal force, I've got gravity, and I've got the y component of the 5 Newton force. Okay, so I'm going to write all those down. Now be careful of your signs. I chose down to be positive, so I'm actually going to start with that one. I'm going to write 196, it's a positive 196, plus Fn is in the negative direction, so I'm going to put negative Fn, plus Fy is also pointing up, which is the negative direction, so I'm going to put negative 5 sine 35 equals mass. Okay, so here's where we're going to assume. We're going to assume that doesn't leave the ground, okay? Okay, doesn't leave ground. I'm writing this bigger because it got all weird over there. Now I'm going to make this assumption. I'm going to show you how you'd know if you were wrong. Because if it doesn't leave the ground, that means in the y direction, it does not accelerate up. And I know it can't accelerate down because there's a floor in the way. Okay? So if you make the assumption that it doesn't leave the ground, then ay should be 0. Which means when I write that in here, I'm going to write in mass times 0, like that. And that would be my next equation. Now here's how you tell if you were wrong about that. Now that I have this equation, the only thing I don't know is normal force. So I'm just going to solve for normal force, and I'll show you how you'd know if you were wrong about your assumption. If I solve what I've got right now for normal force, what I end up with is, okay, I would end up with Fn equals 193 newtons. Now, on my calculator, this is a positive number. Remember in the last video I said, like, the way that we've set it up, where we've put the signs in here when we're writing Fnet, if you're solving for force, you should get a positive answer, because you're finding the magnitude of that force, essentially, when you set it up this way. If you had made the assumption that it didn't leave the ground and AY equaled 0, and you did this work and you got that normal force was a negative number, that means you made the wrong choice. It did leave the ground. Or, well, yeah, it did leave the ground. Basically, it's because of this part. You got your 196 here minus the pulling up off the ground part. So the 196 is pushing the box into the ground, and the 5 is pulling it off the ground. And then, you add Fn to both sides. If I was pulling it off the ground harder than gravity was pulling it into the ground, I would win and I would pull it off the ground. That's the idea. And to make this balance, Fn would then have to be a negative number. So Fn was not a negative number, which means we're good. This thing does not leave the ground, and therefore there is a normal force because I'm staying on the ground, and that normal force is 193 newtons. Please note that that is less than the force of gravity. Essentially, because you're pulling it up off the ground a little bit, the box isn't pushing as hard into the ground, so the ground is not pushing back quite as hard. Okay. Alright, so this was all step 3. Step 4 was to solve your equation. So we already did one of them. Let's solve the other equation too. If I solve the other equation, now check this out. If I solve the other equation, I'm going to get a negative number for AX. That's okay. Only forces should come out with like a magnitude when you do this. Accelerations will come out with an appropriate direction. So for this one, I end up with, oops, sorry about that, there we go. I end up with negative 0.2, I guess this is a 2 sig fig. This is where I should start rounding to 2 sig figs. I didn't really do it for that one either. If I round to 2 sig figs, it's only 0.20 meters per second squared. Okay, here's why it's negative. It is negative because if I go back to the directions I established, this means that this thing has an acceleration in the negative direction. I called the right negative. So really what I have is that the acceleration is 0.20 meters per second to the right. And that's what you should do, is when you're all done, translate your numerical sign back into whatever you chose into a direction word. Okay, because everybody's going to define their directions differently, but the words like right and left and up and down are pretty objective. Okay, so this was a 2-dimensional, 1-object problem. Next we'll do 2 objects.